The idea of turning nanoscale motion into information feels almost contradictory. On one hand, a nanomotor looks like a tiny mechanical toy, an asymmetric bead twitching in chemical fuel, buffeted by thermal noise. On the other, its very jitter and drift seem to carry a message about the world around it, where gradients lie, how strong they are, how fast energy is being spent and dissipated. To many, these two pictures don't add up. If the motion is so noisy, how can it be useful? And yet a haunting question sits at the center of our proposal. If a nanomotor continuously converts free energy into directed steps, can its trajectory itself be read as a stream of bits, an energy-to-information converter written in Brownian ink? From a scientific perspective, the bridge is thermodynamics. At the nanoscale, every shove from fuel and every tug from the solvent has an energetic price. Every bit of order wrested from randomness shows up as work, heat, and entropy production along a single trajectory. Stochastic thermodynamics gives us the accounting, Jarzynski equalities, fluctuation theorems, thermodynamic uncertainty bounds, so that we can translate motion into currency we understand. A motor that climbs a chemical slope is not merely moving, it is measuring that slope with finite precision and paying for each bit of certainty with dissipation. Doesn't this suggest that what looks like a fidgety bead is, in truth, a meter whose needle is its path? Engineers wrestle with the complementary half information theory. Signals have to be encoded, transmitted, and decoded with limited energy and bandwidth. A nanomotor operated in a controlled microfluidic landscape is a physical instantiation of this trade-off. Mutual information between its steps and the hidden field tells us how many bits per second the motor extracts. The fuel's free energy tells us how many joules per bit we spend. Between these poles lies the middle path, feedback control, where measurement steers actuation in real time. A closed-loop information engine doesn't defeat randomness, it harvests it, rectifying fluctuations to sharpen sensing while respecting nanodynamic costs. Could it be that the best nanosensor is not the quietest particle, but the noisiest one with the smartest feedback? A lesser-known perspective is methodological. Once you stop treating motion as a nuisance and start treating it as data, the lab becomes an encoder channel decoder pipeline. Gradient-on-a-chip devices write spatial patterns into the environment. Catalytic and enzyme motors read them out as biased random walks. High-speed imaging and inference decode the message back into fields and forces. The same videos that once served only to see if it moved now yield work distributions, entropy budgets, and energy per bit figures near the Landauer scale. Change the narrative from fighting noise to accounting for it. And the motor turns from a chemical curiosity into a calibrated transducer. The paradox, then, is that nanomotors are both messy and precise. Out of erratic steps emerges quantitative sensing. Out of dissipation comes information. Out of feedback comes direction without violating the arrow of time. Our program embraces that tension. Fabricate motors that spend energy cleanly, sculpt chip-scale gradients that write testable messages, and build analysis that reads those messages in bits per joule. The haunting question we aim to answer is not whether a nanomotor can move, that much is settled, but how close such a tiny engine can come to the ultimate bargain of nature. One bit of certainty for the smallest possible price. Active nanomotors consume free energy from chemical fuels or fields and transduce it into directed motion embedded in thermal noise. Their trajectories are not merely mechanical paths, but stochastic records about external gradients and constraints. By reading these paths, one can infer environmental variables, effectively converting energetic input into bits about the world. Stochastic thermodynamics formalizes this link by tying work, heat, and entropy production to information measures such as mutual information. At microscales, every reorientation, pause, and burst of speed is a probabilistic measurement of the landscape. Thus, the same joules that propel a motor also pay the thermodynamic cost of acquiring information. The converter is the particle itself. The code is its path. The channel is the fluctuating fluid. The paradox begins when motion doubles as computation. A catalytic Janus particle climbs a peroxide gradient, allowing reconstruction of the gradient's direction and magnitude from its biased trajectory. It is like a search dog whose footsteps, not a digital gauge, write the map of the scent. Landauer's principle states that erasing one bit of information dissipates a certain amount of energy, establishing a floor for information processing. In feedback-controlled colloids, this energetic cost has been verified by measuring work distributions during measurement and erasure cycles. Nanomotors extend this logic from externally driven probes to self-pipered agents with internal energy budgets. Each bit of environmental knowledge encoded in their trajectories must ultimately be paid for by chemical free energy, or exported entropy. The accounting is subtle because propulsion, exploration, and sensing are interwoven in time. Yet fluctuation theorems and thermodynamic uncertainty relations bound the achievable precision per unit dissipation. When energy is scarce, optimal strategies maximize bits per joule rather than speed per joule. Information, not distance, becomes the currency of performance. Comparing peroxide consumption with trajectory field mutual information yields an experimental energy per bit figure, approaching a few tens of K times T. It is like paying a toll in heat for every useful clue the world gives you. Classical microrheology treats particles as passive tracers, whose diffusion reveals fluid properties. Nanomotors invert this paradigm. They are out-of-equilibrium probes that inject energy locally to interrogate their surroundings. Self-phoretic slip, enzyme catalysis, or field-driven actuation create controllable propulsion laws. Because motors choose where and how to sample via their dynamics, their information yield can exceed that of passive diffusion in the same time. This agency turns trajectory design into an experimental measurement policy. The environment, in turn, shapes dissipation pathways and sensing fidelity. Active matter thus becomes a programmable metrological medium rather than mere cargo. Sensing is performed by behaving. An enzyme-powered motor navigates a stepped pH profile and reports the step location sooner than a passive bead would by diffusion alone. It is like switching from drifting with the current to paddling strategically toward the signal. Chemical, thermal, and electric gradients bias motor orientation and speed, imprinting the signal into statistics of steps and turns. The cosine between instantaneous velocity and gradient provides a per-step sufficient statistic for direction, while run lengths encode strength. Aggregating many short, noisy snippets yields a decodable message about the field with quantifiable mutual information. Energy dissipation calibrates how confidently a motor can read that message within a fixed time. In optimized regimes, motors trade ballistic exploration for informative sampling of high-grade regions. Microfluidic generators supply ground truth maps to benchmark inference accuracy. Decoding the code path is thus a principled inverse problem, not an ad hoc visualization. From hundreds of short tracks in a known linear gradient, an algorithm reconstructs the gradient slope and angle with less than 10% RMSE. It is like inferring a melody from many brief noisy notes played by a wandering violinist. Stochastic thermodynamics enables trajectory-level bookkeeping, mechanical work from self-propulsion, heat dissipated to the bath, and total entropy production. Jarzynski and Crook's relations connect measured work distributions to free energy differences, while thermodynamic uncertainty relations bound estimated precision by dissipation. With calibrated drag and known fuel chemistry, one can close an energy budget per motor and per cycle. Deviations from bounds reveal unaccounted channels. Slip heterogeneity, catalytic side reactions, or wall effects. Crucially, the same records support estimating information flow, allowing direct tests of information thermodynamic equalities under activity. What appears as jitter becomes a ledger of microscopic economics. Physics of guessing acquires a meter. Single motor movies at 200 FPS yield entropy production rates that coincide with TUR predicted minima for the observed chemotactic current. It is like auditing a company by reading every receipt, not just the annual report. Real-time tracking and microactuation turn nanomotors into Maxwell-style information engines. By nudging orientation only when fluctuations align with a target, feedback rectifies noise into directed work with a measurable information rent term. The added drift is bounded by the rate at which the controller acquires reliable bits about state. Implemented on a microfluidic chip, such daemons compare favorably with passive feedback traps because propulsion supplies part of the energy budget. Performance is reported as bits per joule, watts per bit, and improvement in detection fidelity per dissipated joule. When the controller is silent, motion reverts to unbiased exploration. When it listens, noise becomes resource. A GPU loop applies brief electric pulses contingent on heading, boosting upgrade speed by 30% at fixed fuel flux, while satisfying information thermodynamic inequalities. It is like tapping a sail at just the right gusts to capture wind without rowing. Two platform experiments crystallized the concept: gradient sensing by trajectory inversion and feedback ratchets that lift loads or cross thresholds with minimal energy. Standardized figures of merit couple energetics to information, bits per joule, energy per bit, and Fisher information per dissipation. Libraries of motors, sizes, caps, enzymes, and programmable gradient foundries allow systematic scaling studies. Comparative baselines with passive beads expose the value added by activity. Open datasets of videos, tracks, and energy/information ledgers enable community benchmarking. The deliverable is a yardstick for active information transduction, not merely faster swimmers. Metrology replaces metaphor. A peroxide climbing motor array maps an unknown plume and reports an energy-normalized information rate superior to passive probes. By an order of magnitude, it is like rating cars not by horsepower alone, but by kilometers of reliable navigation per liter. Unfounds include unnoticed background flows, catalyst aging, enzyme denaturation, and wall and juice slip. Each can mimic or mask information gains. Rigorous controls with inert beads, deactivated motors, inverted gradients, and shuffled labels must drive measured mutual information to zero. Energy inputs must be independently quantified, fuel assays, oxygen sensors, to avoid phantom efficiency. If fluctuation theorems fail systematically after accounting for sampling and calibration, the framework must be revised. Likewise, if optimized passive probes match active bits per joule under identical constraints, the advantage of activity is falsified. Clear, pre-registered metrics and open code prevent cherry-picking. A paradox worth having must be disprovable. Running the full pipeline on dead motors yields non-significant information estimates and breaks any apparent advantage, validating the analysis chain. It is like checking a compass in a Faraday cage before trusting it at sea. The paradox is that a nanoscale engine is also a nanoscale sensor, and every joule burned can be counted in bits learned. Motion, usually filed under mechanics, becomes message, usually filed under computation. Thermodynamic bounds migrate from thought experiments to chip-level devices with knobs and readouts. If activity truly buys more information per joule than passivity, design principles for low-power microsensing, diagnostics, and adaptive materials follow. If not, nature reminds us that guessing has a universal price. Either way, the union of motors and information tightens the bridge between energy, entropy, and knowledge at the nanoscale. Behaving is measuring and paying is understanding. A feedback-guided enzyme motor that reveals a toxic gradient faster and with lower energy per bit than any passive bead exposes the trade at work. It is like learning that footsteps themselves, costly, noisy, and small, are the truest instrument for finding home.